Hello everyone, I'm Lukas. I'm working on Tilebox and we are building a space data native tool to help hopefully make your life a little bit simpler. And today I'm gonna dive into one specific challenge which we managed to solve in quite a neat way, and that's related to many of the talks we already had yesterday here in this track too. And that is the problem of spatially indexing your metadata catalog. And I'm probably not the only one here who has struggled with this a lot. It's a common frustration. You have all of these nice metadata catalogs with millions of data points, but you just want to query some small area, and it's quite easy to go wrong here and make mistakes, but it doesn't really have to be. So our idea was that it's time for an upgrade here. And I will show you in a bit what this looks like. But before we do that, let's dive a little bit into what it actually means to build a spatial data index. So our goal is to find a way to make queries for our metadata catalog that has a spatial dimension really fast. And to make this work, we have to build up a spatial index. So for any target query, we want to quickly find all of our scenes that actually intersect our area. And typically, the way this is done right now is often by first, we'll make our lives a little bit simpler by computing bounding boxes for all of our geometries, because working with these rectangular areas is just a little bit easier. And then the next step is we try to group nearby bounding boxes together. What does nearby mean though? How do you define these nice groups? That's actually not a trivial problem, because those are, the geometries are on 2 dimensions. So if you want to try to group them, you have to decide what does it mean for 2 geometries to be nearby. You can try to sort them along 1 dimension, like the x dimension or the y dimension, but as you can see here, you will always end up with some geometries that are grouped together that are literally on the opposite end of the Earth if you do it this way. So we want to find a different way of grading these groups, and there's quite a neat trick you can use here, which is to employ space-filling curves. In this case, we have a Hilbert curve, which mathematically speaking is a continuous fractal. You can zoom in, and it gets arbitrarily more precise. And what you can do with this, you can actually overlay such a curve on all of your geometries, make it in a fine enough precision that it intersects all of the centroids, which is the metric we want to group them by. And now we can compute the position of each geometry centroid on the curve. And this position on the curve becomes the metric by which we grade our groups. And if we do it like this, speaking of a Hilbert sorted data set now, we actually end up together with groups of geometries that always are located quite nearby on no matter what kind of planar geometry you are speaking of. And now that we have these nice groups, we can again compute bounding boxes for those groups. And if we then have a query that is interested in some certain area, we pretty much can skip a whole bunch of groups immediately if the bounding box of the group doesn't intersect the bounding box of our query. And this exact technique here is pretty much what powers the GUParquet row group bounding box filtering that already was presented yesterday in a couple of talks and touched upon. And you can even take this technique a step further, and you can group your groups again, and you can do this recursively. So you compute again bounding boxes for the upper hierarchies, and what you end up with if you do that is a Hilbert R-tree, and that's the spatial index, for example, used by the flat GeoBuff format. However, there is a couple of limitations with this approach. The first is related to bounding boxes. So I'm not sure if I'm the only one who has managed to produce visualizations such as the left one, when your polygons start crossing the anti-meridian, but with bounding boxes, this is always a bit of an issue. And similarly, stuff are really difficult if your geometry actually covers the pole. If you think of this ring on the right, if you take only the coordinates at the exterior of the string, they all share the exact same latitude value. So if you compute the bounding box from minimum latitude to maximum latitude, it's an empty geometry, which doesn't help you at all in indexing. And also, if your geometries get really large, like the full swath of a polar orbital satellite, if you think about computing a bounding box for this, well, what you end up with is the whole globe, actually. So if you want to try to build an index on geometries like this, you won't get far if you just work on bounding boxes. And there also comes a bit of limitations with the tree structure. I mentioned flat geobuff earlier, which uses this, and it works great for their use case because flat geobuff is actually static. So if you insert new data points, you have to rewrite the whole data set. And that's kind of annoying if you have a use case such as ours, where constantly new data is added to your data set. You don't want to rebuild your whole data set all the time. And also, if you have a query on a spatial dimension and you have your index on the spatial dimension, this is really great. You have your Hilbert tree built up to quickly try to narrow down the granules you're interested. But now you have another query where you also add another dimension, like a time dimension. But your tree indexes the whole data set over the spatial dimension, so you can't really make use of the time dimension in the query at all. You would have to build separate trees where you include the additional dimensions at certain nodes. So that's one thing you could do here. But then it quickly becomes complex maintaining these tree structures. So there's quite a lot of limitations with this approach. And one additional one is that we didn't want to rely on one particular backend or storage engine or database that has this already implemented, because for Tilebox, our system is actually designed to run both on the ground and in orbit. So on the ground, we have a database backed by a ClickHouse, and in orbit, actually, we have a very lightweight standalone version of our service backed by SQLite, and our indexing should work in both of those cases. And so the other limitations about the bounding boxes, what we have is a managed catalog, so to say, allowing users to ingest arbitrary polygons. And those may very well spawn over the anti-meridian or cover a pole, so we can't really make any assumption about the nature of our data sets, so we can't do common bounding box optimizations like you could if you know you only have building data sets that are with really small geometries, for example. So how did we go about fixing all of this? And it turns out you can get quite a lot of the way there if you use a really neat indexing method, and that is S2 geometry. So the way this works is S2 defines a cell structure on the Earth, which is just a couple of cells, and each cell is subdivided into 4 subcells at the next resolution level. And you can continue this all the way down up to a level of 30, where each cell is like 30 centimeters on the Earth, basically. And this all starts with 6 initial cells at level 0, and then to, I don't know what order of magnitude, how many cells you have at the finest resolution of level 30. And another really neat thing about this, and that also explains why there's actually 6 face cells at level 0. S2 makes quite a nice assumption. The Earth is a cube. So basically, if you zoom out large enough, you see this cube structure of S2. And this is also really neat, because if you have your indexing as a cube, you don't have any issues around the anti-meridian. You don't have like those coordinate crossings there. And also the poles are neatly covered by some of those cells. So that's why S2 was a really great choice for our use case here, compared to, say, GeoHash or other similar approaches. And within one cell, so each cell in S2 actually is defined by a cell ID, which is just a 64-bit unsigned integer, which is really great to work with if you want to add that to your database, because creating database indexes on integers is pretty much what they're optimized for and what you can get really great performance out of. And this S2 cell ID has some other really neat properties. So if you look on the right on this image of the cells, you maybe notice a familiar pattern, and this is the Hilbert curve we had before. So S2 actually numbers cells by their position on a Hilbert curve, and cell IDs are encoded in such a way that one cell belonging or like being a subcell of another one, you can really quickly verify this by just performing an integer range check, which is again really fast. So how can we use this to our advantage? Whenever we want to insert a new data point into our data set, we start off by computing the minimum bounding S2 cell that fully contains our polygon. In this case, I have a small building here, the Glyph Lodge actually, where we are at the moment, and next to it, the minimum containing S2 cell. So this is just the notation S2 uses how to encode this cell, but in reality, that's just a uint64, right? And it doesn't matter really that it's not a tight fit as it is in this case, because you don't need to, at indexing time, decide on some resolution level of S2 that you want to use. You can freely adapt to your geometries. So this works exactly the same if you have like way larger geometries. Like here, the bounding box is the whole country of Peru, actually, and it still fits really nicely into one S2 cell. However, obviously, most of the time, if some geometry crosses the bounding of two cells, you just use the cell one level up that encompasses both. However, this stops working if you're already at the root cell level, which is the case if your geometry crosses one of the edges of the S2 cube in this case. We have an example of this. The city of Tamba in Japan actually lies on the corner of the S2 cube. So if you have a geometry that crosses or encodes the admin boundaries of the city, you can't find one cell that fully contains the geometry. So this is an issue if we also want to be able to index that. So there's actually a couple of ways you could deal with this. You could just cut it up and split it into 3 different cells and just duplicate your data. Then after querying, you deduplicate it again. You could come up with some special cell IDs for those edge cases. Or the actual simplest approach we came up with, and that worked already quite performant for this case, is for each geometry, we also keep track of which of the 6 face cells it intersects. And then we limit all our queries just to those, and you can really easily store the number of face cells it intersects as a bit mask, which again is quite efficient when you put it in a database. So how do you run a spatial query now? When you have some query area, you do exactly the same thing, right? You compute the minimum containing S2 cell, and now basically your query just becomes an integer range lookup between the cell of your query area and all of the cells of your spatial index. So in this case, for example, our index dataset contains the 3 examples from before, and I added 2 more, another building, the Utah State Capitol, and then another one, a larger one, the entire state of Utah. And our query, it's a bit outlined on the right how this integer range lookup can look like. But basically what you end up with is an approximate result set, which already filters out quite a lot of the data set. And for many use cases, this may also already be good enough. Like if you want to do some visualization, you don't really care if you have some more data that's not even visible, so you don't even need to filter any more than that. But obviously, we do want to eliminate those false positives. And since we talk about arbitrary geometries and not just rectangles, this means we have to do exact geometry intersection checks, which typically is quite slow. So we can speed this up a little bit. And one quick optimization we can do here is to just skip all the true positives if it's possible. And we can do that by also computing an interior cell covering, like the largest S2 cell that's contained within our geometry. And we also do that during indexing for all of our dataset geometries. Because if we have an intersection between the two interior cells, then we know for sure that the polygons also intersect. So we can actually skip all the expensive polygon intersection checks here. And another simplification we can do is just straight up line simplifications, reducing the number of vertices of our polygon. Often case, they are encoded in way too much detail. And in this case, that's like a Sentinel-5P swath from the Copernicus data space, encoded as 300 vertices. And you can get rid of 90% of those and end up with pretty much the same geometry, like when it comes to querying at least. So that also speeds up our exact geometry intersections by quite a bit. And if your query area crosses one of the face cells, what you can do is you just split it up and you add both of those cells, or both of those containing cells to your query. So in this case, you have two integer range checks instead of just one. So why is this really neat to have as your whole index as just an integer column you can add to your database? Well, pretty much all database backends support building trees or like indices on integer columns. So you can just use Postgres, Alloy, or SQLite even, and let it handle all of the tree building and the indexing mechanisms. You can even define multiple indices depending on your query patterns. And it also works good for columnar storage engines that have like data skipping indices. That's like kind of related to the GeoParquet row group concept, but we are using ClickHouse, for example. They also have a concept similar to this, and it works really great here. So let's take a quick look at what this can look like in practice. Here it is. So basically as a test case for ourselves and also as a good way to start exploring Tilebox and our capabilities, we do offer some open data sets. In this case, for example, the full Copernicus metadata catalog. And one of those data sets is like Sentinel-2. And you can see we have like over 100 million granules ingested and tracked and indexed here. And we do keep up with it and ingest new data all the time. And we can now try to use this and run a spatial query on this Sentinel-2 data set here. The way this looks like is you define your query area. In this case, rectangles are kind of boring. That's what everyone's doing. And since we are not doing that, I chose some alternative use case. Here I'm interested in all Sentinel-2 granules in the full year 2025 up to date that cover somehow the US coastline. So I define my query area as a multi-polygon of the coastline. And now I can run my spatial query. And you already see, now we get a nice X-ray data set with 1,600 results and not even a second of query time now. And if we visualize this, then we can already see all of the results. And if you hover over it, you see the individual bounding boxes. So that's how you can use these spatial queries. And I have another small example here, which is another query that's like an area in the middle of the Pacific, which is notoriously difficult to query since that's exactly crossing the anti-meridian. So the way this works, like for a visualization, then now we split it up into a multi-polygon with two parts. You have some results here and some results here, and all of that works still quite neatly. And for comparison, where we source the data from, Copernicus data space, I'm not sure if you've done this as well. It's been a pain point for me a lot when working with these data sets before, trying to run similar queries here. What you often get when you try to do this is kind of long responses. And I mean, a read timeout is not really what you want to get if you just run a standard spatio-temporal query. And you can increase the timeout here. And in my testing, it took around 15 seconds to get a result, but that was just the first page, because then you have to do pagination as well. So it was up to 2 minutes to run a similar query against Copernicus data space. Yeah, so that's pretty much it for the demo. And I really invite you to try it out yourself. So our Tilebox console, which I quickly showed before, you can sign up there for free. You can even create your own data sets, define your schema, and if you have your X-ray data set or your GeoPandas data frame, you can just ingest it and then run queries against your own data sets, or even queries like the Sentinel Copernicus data space that we just showcased. And I really invite you to try and push us to our limits. I'm always really interested in all the edge cases that come up with here. And I'm sure I'm not the only one who has seen really weird geometries out in the wild. So I'm really curious if you can come up with something that our index doesn't manage to find. Please let me know. I would be really curious if such edge cases exist. That's pretty much it. A small shout out for the next track. I actually have another talk coming up about another part of Tilebox, our workflow orchestrator. So if you stay around in the next session in this room, then I can also share a little bit about another cool, exciting project we are building. Thank you. That was it.